try to flip, it works. Good. Okay, hello, good morning. Welcome to the lecture on DAG-based DOTs. Effectively, it's two lectures, one after the other. So, what is DAG, directed acyclic graph? Why do we need directed acyclic graphs instead of chains? So, let's take one step back and review what we already know. Consensus, we already know that consensus is the main bottleneck in blockchain. It has slow convergence, it limits the throughput of transactions, and it can also be resource consuming. I'm talking about open blockchain, right, not Hyperledger. So we already had a lecture where we consider different ways to overcome the scalability barrier. And one of the directions for scaling the technology is to increase parallelism. So one of the reasons for the low throughput of transactions in Bitcoin is the need to serialize the blocks. But what if different nodes can add new transactions concurrently? Okay, some of the transactions may be conflicting. They could be double spending, for example. But not all transactions are related to each other. And effectively, why would we need to agree on the order of non-conflicting transactions? We can include all of them in whichever order. So we'll have only, we only need some partial order, partial dependency between transactions. And furthermore, we can proceed optimistically and roll back in those rare cases with conflicts. Therefore, we could increase the level of parallelism. And if we do that, we get a higher transaction throughput. So using directed acyclic graphs is one of the mechanisms to achieve that. So we'll start with the consideration of IOTA, which is one of the most prominent DAG-based blockchains. Like 5 years ago, it was among the top 10. Now today it's not doing so well. So University of Oslo maintains an MOU with IOTA. So you can see its logo on the slide or on the shirt, which was given to me by the research director of IOTA. But okay, what is IOTA? In IOTA, there are no blocks. Each transaction is stored individually. In transaction, there is no ledger. Ledger in the sense like sequence of blocks. Instead, transactions are stored in a database. So all the info about transactions and balances is kept in the RocksDB database. And individual transactions are organized in a DAG rather than chain. So throughout this lecture, I'll make a distinction about the terminology. Throughout this lecture, I'll say nodes and vertices. But when I say nodes, I refer to network nodes, to machines. When I say vertices, I mean vertices of the DAG, of the graph, which represent transactions. So, not to be confused, nodes and vertices. So in IOTA, each vertex represents a transaction. Of course, this organization requires more storage, because now we need to keep track of the there would be more edges between the vertices, and also each transaction needs to be stored as a separate vertex, and that results in a higher storage requirement. So compared to, say, Bitcoin, IOTA requires more storage. So what's IOTA solution? To do some periodic snapshotting. So the periodic snapshot process removes all of the transaction history and the addresses with zero balances, so a bit of a cleanup, and creates the list of addresses with a non-zero balance. So effective this way, this mechanism of snapshotting allows IOTA to forget about significant portion of the history long gone, and instead of going back to the Genesis block, it would start from some checkpointing from the snapshot vertex. What's the problem? The problem, of course, who does the snapshotting? So snapshotting process requires some degree of centralization, and that's the disadvantage. More about IOTA. So in IOTA, nodes do not create competing proposals for updating the ledger. Instead, whenever a node wants to issue a transaction, it just issues a transaction. Okay, I'll explain. It's more complicated than that. Of course, I'll explain the exact mechanism for creating a new transaction and a new vertex in a DAG. But the principle is simple. There is no batching of transactions into blocks. And if a node wants to issue a transaction, it would execute some algorithm to build the edges. It would create a new vertex, and it would broadcast the vertex. And hopefully every other node in the network would append this vertex to the graph. Okay, so there is no mining, and there is no mining rewards. However, there are some mechanisms. For example, it's an open network. We still need to protect against denial of service attacks. So in Bitcoin, the mechanism which protects against denial of service attacks is POW. However, POW in Bitcoin, so just to recall, POW in Bitcoin serves two purposes. One purpose, to protect against denial of service attack, and the second purpose is to facilitate consensus. In IOTA, the second goal is eliminated. So in IOTA, there are crypto puzzles, but they are only for protection against denial of service attack, and therefore they are much more lightweight compared to crypto puzzles in Bitcoin. And they do not burn nearly as much energy. So I'll call it minor crypto puzzles. Let's take an illustration of how it looks in IOTA. So this is an illustration of IOTA DAG. There is a Genesis block. And then, okay, each bundle, like IOTA at some point initially was using the concept of bundles, which they later abandoned. I mean, you can, for the sake of simplicity, you can assume that a bundle is simply a transaction, even though it has a bit more complex representation. Okay, so the Genesis transaction, and then we have new transactions, and each transaction, as you can see, may refer to up to two previously existing transactions, previously existing vertices in the graph, right? Something you can immediately see, each transaction has a weight, and I'll explain the meaning of the weight of a transaction soon. So, so this is, by the way, double spending. So here and here we have a double spending transaction, which exists in two different sort of branches. I don't know. Yeah, I guess we can call it branches of the DAG. Something else. You can see that most of the vertices have incoming edges, but the most recent ones do not. So the most recent vertices without incoming edges are called tips of the DAG in IOTA terminology. So how are edges formed? So an edge signifies an approval. So whoever issued, say, transaction H, saw transactions F and E and verified their correctness. And in order to confirm that, it's like a signature. In order to confirm that, the issuer of transaction H put these two edges, which signify approval of these two transactions by the issuer of transaction H. Okay, we are going to see more of such diagrams soon. So what you see here is well, it's not a ledger. In IOTA terminology, they use the word tangle to refer to this DAG-based structure. So they do not say ledger, they say a tangle. But effectively, it's a DAG. So the DAG is replicated on 3 nodes in the network, in this example. And you can see it by coloring. So different nodes in a distributed system can be out of sync with respect to each other, which means that at any given moment in time, each node would see a slightly different picture. All nodes would know about the genesis block or the genesis transaction. But not all nodes would know about the most recent transactions, right? And this is the reason for the divergence in views. It's called a view of the node. So here we have 3 different views. This is the view of node 2, this is the view of node 1, and this is the view of node 3. Okay? And this is a new bundle, which is not part of the new transaction, which is not part of the DAG yet, but which is about to be appended to the DAG. These are tips. Again, this is the double spending bundle. And the creator of the new transaction needs to decide. It can only approve a tip, but it needs to select which of the tips it wants to approve. So here's the algorithm for creating a new transaction and extending the tangle accordingly. So a node who wants to issue a transaction would need to create a new bundle and would need to decide on a weight for the bundle. And in the basic implementation, a node can autonomously decide on the weight of the bundle, which is just an integer. Okay, so what's the meaning of the weight? The difficulty of the crypto puzzle, we said it's a simple crypto puzzle. Yes, it is, but its difficulty is linearly proportional to the weight of the transaction. Okay, so this limits the weight from above, right? So why would the node pick a non-zero weight or a large number? Because a bigger weight results in a probabilistically faster confirmation for the transaction. So essentially, the issuer of transaction needs to decide if the issuer wants to go for a fast confirmation and then put more resources into the crypto puzzle, or if the node doesn't care. And then the node can assign, it cannot assign a zero weight, but it can assign a weight of 1. I believe this is the minimum possible value. Okay, again, the issuer creates a new bundle, decides on the weight, solves the crypto puzzle, whose difficulty is proportional to the weight, and then it needs to decide which two existing tips to approve. And the algorithm to do that is actually quite elaborate and not simple. Normally, each new bundle, each new transaction refers to two tips. That's the normal situation. But of course, sometimes there is only one tip in the DAG. It may happen. For example, in the beginning, there is only the Genesis transaction. But even later, there could be cases when there is only one tip available, in which case the node would have to restrict itself to selecting only one tip. That's an exceptional case. Okay, suppose the creator, the issuer, has selected two tips. The next step would be to validate all transactions on the two paths. It's not only selecting the tip itself. The issuer also needs to select a path from the Genesis transaction to that particular tip. So the issuer has two paths. And now it needs to verify the correctness of all transactions on the two paths. So what does it mean, correctness of transaction? Well, it means, of course, that they're structurally formed in a correct way. But it also means that there is no double spending. And if there is a problem, for example, double spending is detected, then the selection algorithm for the tip and for the path is performed anew until the issuer finds a correct path. Okay, so finally, the issuer finds two correct paths. At this point, it sets the two edges, and it propagates the new transaction with the two tips throughout the network. And every receiving node performs a chip validity test, checking just the integrity of the bundles along the path. So it would not be checking the double spending. Which means that double spending can effectively creep in if the sender is, or if the sender of the creator of a bundle is malicious. It may introduce double spending. Or rather, maybe not introduce double spending, but it may confirm two transactions or two paths which include double spending. However, probabilistically, this case will be discovered later when someone else would try to add, when an honest node would try to create a new bundle and try to approve. At this point, it would do the detection and discover that there is double spending. So what happens in the case of double spending? There is no punishment. What happens is the following. Okay, I'm going to say soon what happens in case of double spending, but there is another step. The creator of the transaction needs to perform monitoring of confirmation and retouchment. I'm going to explain that step soon. So this is the same DAG. So now we can see how it works. The selection of the tip and of the path is what's called a random walk algorithm. What is a random walk algorithm? So some of you may already know, but I'll explain. Random walk algorithm means I walk on the road, I come to the crossing. Now I have several ways. I can go to the left, I can go to the right, I can go straight. I flip the coin and I decide which way I go. Okay, I selected left. Next crossing, I flip the coin again. And I continue this process. If the graph contains loops, I can go indefinitely in the loops. However, in a directed acyclic graph, it doesn't have any cycles. So the process would always stop. All right? Okay, so how does IOTA use this algorithm? The random walk always starts with the genesis block. Now from the genesis block, I can go to bundle A or I can go to bundle B. Which way I choose, I flip a coin. However, the random walk in the IOTA is weighted. What does it mean? Bundle A has the weight of 1, but bundle B has the weight of 3. It means that bundle B gets 3 times as high of a chance to be selected as bundle A. So I flip a coin, but the selection is not uniform. It's governed by weights. And that's why the random walk in IOTA is called weighted. Okay, suppose I selected bundle B. Then, from bundle B, I can go to bundle C or bundle J. I toss another coin, select C. Even though C is less likely than J, it has a lower weight, but the selection is random. Next step, I select bundle D. Next step, I select bundle F. By the way, from bundle G here, I had only one choice. Then select bundle G. And, and here I stop. Now, this is how I find one path and one tip. I repeat this process twice, and then I select the correctness. And if it happens that on the second time I will go this way and hit bundle D tag, D prime, at this point I detect double spending. Okay, so what happens in the case of double spending? And not only in the case of double spending. So some bundles are getting confirmed. Because of randomness, some bundles may get confirmed much faster than the others, while some valid bundles may in fact be never confirmed and be left behind in IOTA terminology. So this is an example. This is a tip which is left behind, because you see here everyone references, all the vertices reference each other, right? So it's like a cluster. But this tip was left behind. Maybe because it has too low of a weight compared to the other tips. That could be one reason. Maybe someone wanted to start starve that particular tip. So there could be different reasons. But anyway, it's left behind. So if it's left behind, if it's not sufficiently confirmed, that you cannot be sure that it will go in. You cannot, like, what about transaction finality, right? You can ask. Well, it's probabilistic in IOTA, just like it is in Bitcoin. Well, the computation of probabilities is totally different. And it can always be that even though your transaction was successfully appended to the DAG by many nodes, it's still possible that this transaction will be left behind. So in practice, I can only be sure that the transaction is valid after some time if there are enough of later transactions that build on top of the old transactions. So the confirmation in IOTA is also quite a complex algorithm, right? Because we take some old transaction here, and then we need to wait until there is sufficient weight, later weight. So we calculate the cumulative weight of later transactions which approve the given transaction. And if the later weight may exceed some threshold, then we declare a victory. We declare that the transaction is final. Okay, so it means that after you issue the transaction, you are interested in the transaction, you need to monitor the DAG for not only for inclusion of the transaction, but also for later approvals of that transaction. And the speed of confirmation depends on the weight of the bundle, of course. And here comes the additional mechanism of reattachment. At any point in time, a node may repeat the same transaction. How do we know that it's the same transaction? Well, it would have the same transaction ID. So this way we know that it's not like Alice transferred one IOTA token to Bob twice in two different transactions, but we will know that it's the same transaction because both transactions have the same ID. Okay, so it's called a reattachment mechanism. The same transaction can be injected by the same node again at a later point in time. Why? Because maybe the first transaction was left behind. So it got never confirmed. Then we need to, it's called a reattachment. We take the same transaction and attach it in a different place in the DAG. And this is something that also happens with double spending. If there is double spending, then after it's discovered, one of the double spending vertices will be left behind. It will not be confirmed. What about attacks on IOTA? There are quite interesting attacks on IOTA, I would say. The first one is called parasite chain attack. An adversary secretly generates an alternative subgraph offline, but occasionally references the main graph to obtain a higher weight. So you see the illustration here. This is a parasite chain, and this is the main tangle. So the parasite chain is never confirmed for the time being. And there is double spending transaction. You see, in a parasite chain, the double spending transaction was there from the very early stages, almost from the beginning. And then later, the attacker injects a double spending transaction. Much later, the attacker would inject a double spending transaction in the main chain. So of course it gets confirmed in the main chain. Of course, I mean, most likely it gets confirmed in the main chain. So the attacker would get some goods or services for that transaction. And at this point, the attacker would release all the vertices in a parasite chain. What's the idea? The idea is that because there is so much weight in the parasite chain, it will likely be confirmed, and while this transaction is just a new transaction, then it's likely that the newly appended bundles or transactions would approve the parasite chain and not this one. So the double spending will be detected, yes, but at this point, this transaction will be left behind, while the parasite chain will become legitimate part of the main chain. And as a result, so first the attacker gets something gains something in return for this transaction. Then this transaction will be left behind, and then the attacker gets some goods or services as part of this transaction. So it's a variation of the double spending attack, but in the DAG-based world. More attacks on IOTA. The next attack is called a splitting attack. I mean, the attacker partitions the tangle by making sure that the two subgraphs within the tangle maintain a similar cumulative weight over time. And then this balance needs to be maintained, right? So the attacker would need to inject transactions in order to maintain this balance between the two partitions of tangle. Okay, so what's the point? The point is that such partitioning allows the attacker to perform double spending by placing two conflicting transactions, one in each subgraph. So what happens is that there would be some the two branches, the two partitions are competing with each other. And sometimes, because they have almost the same weight, sometimes the first partition would be the winning one, and sometimes the second partition would be the winning one. And they're competing because they have double spending, because they have conflicting transactions. So sometimes one partition is considered the main tangle. Sometimes the other partition is considered the main tangle. And that's another case for double spending. And in fact, in such a situation, again, the trick, of course, for the attacker to maintain this partitioning. But if the attacker manages to do that, then it can inject several double spending transactions, not just one. So two copies, one in each partition. How do we defend against such attacks? So there have been some tweaks or slight modifications to the IOTA algorithm. The first modification was to modify tip selection so as to increase the chance of left behind tips. How do we do that? We can increase the chance of having left behind tips if by slightly changing the random walk algorithm. So the basic idea of random walk is So suppose we need to take a decision. Suppose we have weight 1 and weight 2. So vertex V1, or okay, let's say transaction TX1 has weight W1, and TX2 has the weight of W2. Okay? In this case, so the basic algorithm selects TX1 at the intersection, right? It selects TX1 with the probability linearly proportional to W1, and TX2 with the probability of probability which is linearly proportional to the weight 2. However, it doesn't need to be linearly proportional. We can introduce, for example, quadratic dependencies, right? We can say the choice is proportional or will be proportional to W squared instead of W. If we do that, then the weight would have a stronger impact on the selection. Slightly higher weight would result in more significant impact compared to linear dependency, right? So we have the freedom of how to do the weighted walk. And okay, so it means that the bigger weight would have an even higher chance to be chosen. And this mechanism would increase the chance of left behind tips. So doing that has been proven to improve protection against splitting attacks. However, the negative effect is that it increases the amount of left behind tips. And then it increases the need for retouchment mechanisms, or retouchment would need to be done more often. Right, so the DAG grows, there is higher overhead related to left behind tips. So there is a trade-off here. Another question we may want to ask is about the incentives of nodes in IOTA. There are no rewards, as mentioned, for mining. There are no transaction fees. So the question of incentive arises. Why would the nodes do what they are supposed to do? Why would the nodes correctly follow the algorithms? Well, I mean, in general, the assumption is that most of the nodes would be interested in correct functioning of the system. But not only that, each node would be especially interested in acceptance of the transactions by that node. So there is an incentive, and the incentive is based on the acceptance of transactions by the node itself. So how does this incentive apply to different cases? What's the overhead? The overhead is to compute POW, short crypto-puzzle. Okay, the node would need to do that in order to get the own transaction confirmed. So the node would want to do that. The node would also need to execute this complex and maybe computationally expensive, well, it's not very expensive, but at least it's non-trivial random walk algorithm. Why would the node proposing a new bundle or transaction want to execute the random walk at all? Why not select some random tips instead of doing the random walk? the node could save resources if the node could just pick the tips randomly, the two tips randomly, instead of executing the random walk. So why would the node do the random walk? And the reason is that probabilistically, the tips chosen by the node have the highest weight. They have higher weight than had a higher cumulative weight compared to the other tips. And therefore, it's very likely that whoever wants to append a new block later, new transaction later, would also select the same path. And if instead I pick a path with lower weights, then my transaction will take longer to be confirmed by the others. So that's the logic. Another question: why would the node creating a new bundle perform a random selection instead of just choosing deterministically a tip with the biggest weight? So that's an interesting deviation from the protocol. It looks beneficial at the first glance because that would increase the probability of faster confirmation. So that's a valid attack on IOTA, and the IOTA sort of introduced some additional protection mechanisms against this kind of behavior. Okay, what about performance of IOTA? The typical IOTA throughput has been reported at around 50 transactions per second. So it's better on Bitcoin, but it's not very impressive compared to, say, Fabric. In stress testing, they somehow report 500 transactions, but of course, like, this is not what people have observed in their actual deployment. As mentioned, it requires significantly more storage space compared to a chain-based ledger, but this is mitigated by periodic snapshots. And because of the snapshot, one of the criticisms on IOTA is potential centralization. And another thing is discovery of double spending may take a lot of time, which is a problem, right? Because we want to know if the transaction is final as soon as possible. So let's come back to this table which compares different systems, but now we are looking at the IOTA column. So IOTA is also using UTXOs, not accounts. It produces DAG of transaction bundles with edges signifying approval. Tango is stored in a RockDB database, so there is no like blocks stored in files on disk, in contrast to the other system. So there is additionally, IOTA maintains snapshot data, and the snapshot purges the database. And there is some additional technology in IOTA which provides in-memory storage for faster processing. It's called Tangle Accelerator, which is effectively a proxy cache for nodes. So IOTA was an interesting foundation because it had a research team, and the research team was always coming up with some new ideas. So these are some of the new ideas for IOTA. Increase the number of tips. Why 2 tips? Why not 3 tips? Well, the higher the number of tips, the more the overhead of computing the paths and verifying the integrity and correctness. So some bounds had to be maintained. But of course, like high number of tips, on the other hand, would increase the confirmation rate. Core decide. A mechanism to eliminate the coordinator doing snapshots to increase decentralization. Committee selection. So at some point they were running around with the idea of consensus being run by a committee, similar to Algorand and other systems using committees. A reputation system. So they wanted to introduce a reputation system to individual nodes. And the reputation system would give, for example, mana to nodes according to the quantity of tokens they own. So mana is like a reputation. Or it's like it's similar to proof of stake, but it's different. And node would use the tokens for weights of their bundles and for committee selection. And also, IOTA played around with the different tip selection algorithms and different convergence. Even convergence metric, I mean, again, the question, when should we declare a victory? When can we say that the transaction is final? It's not simple in Bitcoin. To recall, the Bitcoin client declares victory after six subsequent blocks. But this is just a random number, right? So when should we declare a victory in IOTA? That's not a simple question. So there was some research based on that. Okay, so at this point, I would like to thank you, and this is the end of the lecture. Hello, hello, hello. Okay, we'll start with the second lecture, which is essentially a continuation on the DAG-based DLTs. Last lecture we have covered IOTA. Now we proceed to consider to give an overview about other DAG-based systems. So there are three types of DAG-based DLTs. The first type is main chain enhancement. So a lot of DAG-based systems are just trying to improve convergence on the main chain. For example, Ghost does exactly that, right? The Ghost protocol, which we consider in the context of Ethereum, of convergence in Ethereum, does exactly that. Namely, they they use additional blocks, or in the case of DAG-based, it may be additional transactions, which would help compute the weights of the main chain and therefore increase mining utilization. That's the first family. The second family is mostly about sharding. So we shard the large amount of data, we shard the large chain into multiple chains. And then we have several parallel chains. And that situation continues over time. So the parallel chains do not converge. However, they do refer to each other, because there could be cross-chain or cross-shard transactions. So Vita, Nano, and Caper are examples of systems with parallel chains. And in the third category, we have DAG-based systems without predefined structure, like IOTA. In IOTA, the structure, the shape of the DAG is not determined beforehand. It's built on the fly. So one interesting aspect we are going to consider is what kind of knowledge is encapsulated by the DAG. What does a vertex represent? When does a node create vertex? That is, what is the trigger event for vertex creation? Which nodes create vertices? What relation between the vertices and connecting edge represents? So when it comes to edge creation, whenever a new vertex is created, the node creating the vertex also creates backward edges to connect the vertex to existing DAG. So how many of such backward pointers? And what is the way in which the targets of these backward pointers are selected? So let's take a look. Vertex, or let's go over different dimensions and the different choices for each dimension. Regarding the vertex type, there could, like some DAG-based system, maintain transaction and block vertices, which store a single transaction or a set of transactions respectively, along with references. Other systems build event vertices to record the detection of specific conditions pertaining, for example, to synchronization. Yet more systems use snapshot vertices in order to record, to perform and record a snapshot of the current system state. Some DAGs use voting vertices. So sometimes the consensus algorithm itself creates special vertices, which record the instance of voting, say by a majority or by a number of nodes. Okay, what's the trigger for vertex creation? Transaction arrival. In some DLTs, a vertex is created once a new user-initiated transaction is injected in the system. In some other cases, it's based on POW or proof of stake. By the way, collectively, proof of something is referred to as POX. POX is an abstract reference to proof of work, proof of stake, proof of authority, proof of elapsed time. So it means some mechanism to this end. Proof of something. In a technical jargon, in this area, it's related to as POX. So a trigger for vertex creation can be POX based. Once a node generates a proof of work of an allocated resource, it would create a new vertex. Next possibility is knowledge based. A vertex is created once the node acquires knowledge about a certain global condition in the system. Synchronization request. A vertex is created when a node receives a synchronization request from another node in the network. Periodic. In some systems, there are special knowledge consolidation vertices that are created periodically. And finally, pairing. In some DLTs, vertices in a DAC are organized in pairs. For example, a transfer may result in two vertices, one for sending and another for receiving the funds. So far, it's very abstract, but we'll take a look at some systems soon. What are the targets of pointers? What are the potential targets of pointers? It could be all vertices. It could be vertices of particular type out of those types listed previously. In some systems, we pick the heaviest branch and only vertices from that branch. In some systems, we compute clusters of vertices and pick the heaviest clusters. Some systems operate by round, and there are vertices created at each round, right? Like classical BFT protocols, they have rounds, and for each round there are new vertices, and we select vertices of particular round. Sometimes it could be vertices created by a particular node, and there are other cases. Target set restriction, we can create tips paired previous. Now it's getting more interesting. Edge representation. So what is the semantic of an edge? Essentially there are two semantics. One semantic is integrity and the other is validity. Integrity means that if a new vertex points to another vertex, it's like a signature that the older vertex is formed correctly in terms of integrity. And sometimes it conveys some information in terms of validity. Validity means that the previous vertex to which the pointer to which previous tip, for example, to which the pointer goes, is valid. Valid means no double spending. There is enough funds to do the transaction. There are no conflicts. Okay, validity usually means cons validity. So if you take a look at IOTA, okay, I need one of those graphs, so that would be good enough. So usually the edge signifies validity of the cone. What is a cone? Cone means everything that can be reached from this vertex. So this would be part of the cone, this would be part of the cone, this would be part of the cone, this, and this. That's a cone in a graph. So the validity semantic of an edge usually signifies validity not just of the vertex itself to which the pointer goes, but validity of the entire cone. And then, in addition to validity semantics, an edge may also represent voting semantics. So an edge may, from a later vertex, may indicate that the later vertex votes for an earlier vertex in case of conflicts between different vertices. So here's an example. This is the cone of vertex X, vertex H, right? And in this example, the edge may signify that, for example, vertex F would be competing with okay, that would probably not work. Would be a good example. Okay, let's consider vertex G, right? It points to vertices D and F. Now it may be the case that vertex E is conflicting with vertex D, okay? So this edge may signify that vertex G votes for vertex D, and the lack of the edge, lack of the path, in fact, from vertex G to vertex E signifies that vertex G doesn't vote for vertex E. And therefore, between the two conflicting vertices, we need to pick, according to G, we need to pick vertex D. And if all other vertices do the same, then this is how we would resolve the conflict. So here you can see a table with different DAG-based systems: Ghost, Inclusive, Spectre, Ghost DAG, DAG-NIT, Conflux, Nano, Vita, Graph Chain, Hash Graph, Joint Graph, and Byteball. And here you see classification of different systems according to the vertex type, according to the vertex creation trigger, who creates the vertex. So the options here could be any node or could be committee, and it could be committee node. Any node means that any node can create a vertex without any coordination with other nodes. A committee means that committee is selected and committee members need to coordinate creation of vertices with each other. And the committee vertex means that there is committee, but out of the committee, any member of the committee can autonomously create a vertex without coordinating with other members of the committee. And then you can see that the edge has some validity semantics and some voting semantics, right? For most DAG-based systems, the selection method for the edges is random, or rather first known. Like first known means that, for example, I learn about some vertices first. I learn about three vertices, A, B, and C. If I learned about vertices A and B before C, then I would pick edges to A and B if they are all equivalent. And I would not create an edge to C. That's first note. So IOTA is special because it does the random walk. It's the only system which does random walks. So the table analyzes an order of 30 different systems and classifies them from this point of view in terms of the what edges represent and what vertices represent and how vertices are formed. There is also an additional representation pertaining to consensus. So here we have some more basic information about the system. Openness, ordering, and finality. Openness just means if the DAG-based system is permissionless or permissioned. Finality means whether finality is probabilistic, and probabilistic means like in Bitcoin, it never happens, but like we never reach 100% guarantee, but the probability becomes vanishingly small, becomes smaller and smaller with time. So that's probabilistic finality. And deterministic finality is like in BFTs, where there is a point in time where we can say, yes, the transaction is part of the ledger or part of the DAG. And from this point on, the transaction can be considered as final. Now, ordering is another interesting characteristic of DAG-based system. So what does ordering mean? Ordering can be total or partial. Total order means that all transactions in a DAG are eventually converted to some sequential order. Well, that doesn't happen all at once. They may get confirmed even before the total order is introduced, but eventually there would be a total order. At the same time, the partial order means that that total order would never introduce, that there are only some partial dependencies between the transactions, like in IOTA, what we saw in the previous lecture. So it's also interesting to see how conflicts are prevented in different systems. So some systems try to prevent conflicts proactively, while some other systems try to detect conflicts reactively and then try to resolve them later. And if they resolve them, actually in both cases we could use some votes. We could use order between the vertices, or we could use some additional weight-based algorithms. So here you can see a few systems are doing prevention, but actually most systems are doing detection of conflicts. So let's go back to Ghost, which we already know. This is just another illustration of Ghost, right? So this branch is the longest branch, but it's not the heaviest branch. This branch is the heaviest branch. So we already talked about Ghost in the context of Ethereum. However, later there were further development of Ghost. So the main impact of Ghost was on the conflict resolution rule. However, later variations, such as inclusive, did more. So they rewarded creators of blocks in secondary branches. So, for example, in Ethereum, before Ethereum switched to proof of stake, they had the concept of uncles, this concept comes from inclusive. So what are uncles? Uncles are nodes, okay, it's like in the previous slides. Nodes which are not, or vertices which are not on the main chain, so they are not on the main chain, but they contribute to the main chain. Oh, for example, here the main chain may be this chain, while this node would be an uncle. An uncle is not on the main chain, but its weight contributes to the weight of this node. And this is why this node is selected for the main branch. So the original Ghost protocol only used uncles for the calculation of weights. But later protocols also reward creators of uncle blocks. And another impact of the Ghost protocol, so later variations such as inclusive, merge transactions from secondary branches. So imagine, let's come back here. Let's take a look at this block. So its creator would also be rewarded for pointing out that the block would be stored in the ledger, and its creator would be rewarded for pointing to the block on the main chain. So that's like an extra incentive to create uncles. But also, this block may include some transactions which are not on the main chain yet. And there are variations of Ghost, again inclusive, which include transactions from uncle blocks which are not presented on the main chain yet, and they merge them with the transactions on the main chain. So in a previous version of Ethereum, Casper, they borrowed the conflict resolution rule from Ghost, and they rewarded creators of block, and they allowed the block to have one main parent on the main chain and two uncles. And it imposed constraints on how the uncles could be chosen. So another question is throughput and scalability. So scalability means number of nodes the system is able to support, while throughput means the transaction rate, number of transactions per second that the system is able to process. And here each block here represents a different DAG-based system. So as you can see, I mean, the ideal situation, of course, would be here, but most of the systems are not like that. IOTA can have many nodes, like Bitcoin, and it provides, however, its throughput it's higher than that of Bitcoin, but not very significantly higher. And then what we have here, like Caper, it's essentially a sharding system, so it doesn't reach convergence on the main chain. But due to introduction of shards and smart management of shards and smart management of cross-shard transactions, they manage to achieve high throughput. However, they do not scale very well with the number of nodes. So that's another representation of the major trade-off in the design of blockchain systems. So there are quite a few open questions and the research challenges remaining in this domain. DAG-based system is one of the more recent areas of blockchain, and therefore many questions are still unresolved. And a lot of papers are still coming out, research papers in this area. So some examples of open questions and research challenges. How can we support smart contracts based on DAG-based systems? So we can. I mean, there are some systems which definitely support smart contracts. But it's a challenge because ensuring correct state transition is essential for smart contracts. And this requires usually units sorted in a linear sequence for a consistent view. And therefore, only the system designed with linear sorting algorithm has the chance to establish upper layer components such as the smart contract. Next question. Is there a blockchain design that simultaneously scales throughput, storage efficiency, and security? So currently no protocols in the context of DAG blockchain meet all these requirements at the same time. Next question, how can we do snapshot without significant centralization or knowledge consolidation vertices? So knowledge consolidation vertices represent some global conditions that have happened. So it's nice that those conditions can be recorded and represented in the DAG, but of course it inflates the size of the DAG. So, what would be a good trade-off? And in what cases? Like currently there is no recipe, no recommendation which would say you need to use knowledge consolidation vertices in those particular cases. Another question, is it better to prevent conflicts or to resolve them reactively? Most of the systems, as we have seen, most of the DAG-based systems resolve conflicts reactively. But is it because it's easier or is it because it's better for the applications? So there are quite a few open questions which remain in these domains. And this is essentially the end of this shorter lecture. I would like to thank you. Hello, 1, 2, 3, 4, 5. Okay. We are ready to start the third lecture. The third lecture today is on security of blockchain systems. So why are we looking at security? There are many aspects of security in the context of blockchain systems. For example, node level security, so security of individual nodes, bugs related to the contracts, dishonest behavior or self-centric behavior, design problems of the blockchain systems, both at the level of blockchain and application built on top of blockchain, vulnerabilities of the network and misconfigured network, and of course vulnerabilities at the level of the application. So there are many aspects of security and consequently many attacks. So classification of attacks. The attacks are mostly different between open and closed ledger, but some attacks apply to both. So bugs can obviously play a significant role in both ledgers. However, usually the programs running on top of closed ledgers are more developed, they're longer, and probabilistically they contain more bugs. Denial of service attacks are more, so there is a number of attacks which are more typical to the open ledgers. For example, stealing coins. That doesn't happen in closed ledgers. Denial of service attacks. In open ledgers, denials of service attack can be run from within. So a node on the open network can launch a denial of service attack. While in closed ledgers, there is usually core nodes constituting the network and running the ledger, while there are external clients. So external clients, like it's in a database, can launch an attack on the ledger in some cases. But anyway, denial of service attacks are not nearly as typical and not nearly as dangerous in closed ledgers as they are in open ledgers. In open ledgers, there is another attack, like Alice doesn't like Bob for whatever reason, so whenever there is a transaction from Bob, Alice tries to make sure that that transaction is not included in the ledger. So Alice tries to starve Bob. So that is also possible in principle. Of course, there is double spending, and but there are also a couple of additional attacks that we have not talked about much yet, and that's selfish mining and attacks on maximum extractable value. So these two would be the topic for the bulk of the lecture. In contrast, in closed lectures, we have attacks, we have misconfigurations, but we also have some very interesting attacks related to consortia. Imagine that you have a consortia of healthcare institutions. And in consortia, so there would be some hospitals, some labs, some doctors, some pharmaceutical companies. And some of those participants would be complementing each other in order to provide holistic healthcare, but some of those participants would be competing with each other. So if they compete with each other, they may try to play around. So for example, there are two competing pharmaceutical companies offering different medicines against the same, say, the same disease. In that case, and they both participate in blockchain consortium. In that case, if the blockchain is queried, so you cannot eliminate information from blockchain, but you can prioritize information. For example, you can try to order transactions related to the two competing companies in a certain order, or you can supply information when queried. You can supply information. You can, for example, you can try to omit one block from the ledger, and hopefully it would work. So, and that block would include, say, transactions from competing companies. So you can play tricks of that kind in a consortium blockchain. And you can prioritize the responses. So double spending, selfish money, and maximum, especially selfish money and maximum attack, extractable value would be what we spend the bulk of the lecture on. But first, let's do a cursory coverage of attacks on open ledgers. So stealing coins from the ledger is hard because of digital signatures. If, however, someone accumulates a lot of coins, it becomes a prime target. And the difficulty of stealing from a custodial wallet depends on the security of the system providing the wallet, right? So it's hard, but it's highly profitable. And if stolen, there is no way to prove that the funds are yours and not of the thief. There have been many interesting legal cases in courts all around the world where funds have been successfully stolen. So I can tell you about one specific case where I was involved as a technical witness in court. So it was the first crypto exchange in Norway. And that crypto exchange in Norway used a white label solution, meaning a middleware solution, called the Alpha Point. So Alpha Point was a solution deployed somewhere in New York, while the organization using it were spread all over the globe. And in particular, there was one in Norway. And usually in such arrangements, the situation is such that the white label company in New York, Alpha Point, is responsible for the technical maintenance and deployment, while the clients are interacting with the local agencies, local crypto exchanges. So what happened one beautiful day? There was like the Norwegian crypto exchange discovered that some funds were stolen. So then there was an investigation. All the funds were frozen, and you could say the hell broke loose. Okay, so there are two interesting aspects. Okay, first, how did the theft occur? The theft occurred because of phishing attacks. What is phishing? The attacker knew that some person worked for administration of Alpha Point. And then they used, say, fake SIM cards to impersonate, so first of all, they collected all information they could about that administrator of Alpha Point. And then they tried to impersonate that administrator. So phishing attack, instead of sending, say, one-time code to the phone of that administrator, the attacker managed to do that all the phone calls were diverted to a different number. Essentially, after the attacker knew everything about that person, the attacker contacted the phone company and tried to impersonate that person and say, okay, it's me, but now I want to receive the calls on a different number. Or I want call forwarding. And this way, the attacker got, say, one-time passwords. With one-time passwords, the attacker was able to access the private database of Alpha Point, and from there, just steal the funds, transfer the funds outside. So that's the first interesting point, how the attack happened, because it's symptomatic of other several such cases where cryptocurrency funds were stolen. The other part was okay, how was it resolved in terms of the settlement? Well, so the Alpha Point was insured, and that there was proprietary settlement. That proprietary settlement, and then there was a proprietary settlement between crypto exchange in Norway and Alpha Point in New York, thanks to which some funds were paid to the crypto exchange in Norway. However, all this was done behind closed doors, and all of this was confidential. So the clients, the human users of the crypto exchange in Norway, didn't get even this information. All they knew is that their funds were stolen, and then the crypto exchange got some compensation, undisclosed compensation, and then the crypto exchange paid some settlement or offered a settlement amount to individual users. So individual users were very unhappy, and there was a court process for more than 3 years. Eventually went to the Supreme Court. And this is very interesting because it's representative of several such cases in Japan, Brazil, and quite a few other countries. So it's very difficult because it's very difficult to prove that you are the legal owner. The means through which such conflicts can be resolved are very limited. Okay, so that was about stealing coins from the ledger. Now let's move on. Denial of service attack. How do you launch denial of service attack on Bitcoin? Well, you cannot just propose some new blocks because that would require sovereign POW, which would make denial of service attack very costly. But what you can do is to bombard Bitcoin with meaningless transactions. So Alice and Bob decide to launch a denial of service attack on Bitcoin. How do they do it? Alice transfers 1 Bitcoin to Bob. Bob transfers 1 Bitcoin to Alice. Okay, they would still need to pay the fees, but hopefully the fees would be small. And if they produce a lot of such transactions, they could just flood the Bitcoin network. So far it has not happened, maybe because of the fees, maybe because of other issues. Okay, the next attack, starving a specific user. As I mentioned, Alice dislikes Bob, so Alice would do everything in her power to block transactions from Bob. So if Alice is a miner, it's easy, but hopefully each time the block would be proposed by a different miner, and hopefully some of those miners would not dislike Bob. So starving a particular user requires significant amount of coordination, and therefore it's difficult to do. But of course it's possible to blackmail users with high transactional fees if miners are rational, right? So the miner can even out of band contact the originator, the user, and say, well, the fee that you propose is too little. I want a higher fee. So that is possible in open ledgers. Another attack I'm going to mention is called pool hopping attack. And it's, okay, I mean, the general point here is that some of the attacks could be on the mining pools. We saw in the lecture on Bitcoin that individual miners are organized in self-organizing and creating mining pools in order to make sure that their profits are more predictable for a given period of time, so to reduce the variability of profits. Okay, so how does it work? Each mining pool is governed by a pool manager, which gives block mining work to miners in the same pool. And the individual miners in the pool provide partial proof of works and full proof of works to the pool manager. And when one participant in the pool manages to find the solution, the pool manager, so it would give the solution to the pool manager, and then a new block with the solution is broadcast to the network of miners by a pool manager, to get the reward, and then the manager would distribute the reward to the individual miners in the pool. So, usually the distribution is proportional to the number of attempts. So the participants in the pool, they submit partial proof of work in order to show that they are indeed trying to solve the crypto puzzle. And then as a result, like if the pool manager gets the reward, it would distribute the reward according to the attempts to individual miners, according or proportionally to their attempts to solve the crypto puzzle. Okay, then how does the pool hopping attack work? A malicious miner in the pool analyzes the number of shares submitted by other miners in the pool to the manager for finding a new block. So we assume that a malicious miner is able to watch the network, which is possible in some of the pools, and see how many attempts have been submitted to the manager. However, those attempts are submitted not necessarily with the solution. They could be submitted as a proof that the miners do some work in order to get the shares. So if many shares have been submitted, but a new block has not been found yet, then the miner can realize, okay, now I find the block, I will get a very small share from the reward, since the reward is distributed based on the submitted shares. So then suppose the attacker, the malicious miner, is able to find the block. Why would the malicious miner want to submit the solution to that manager? Instead, it might be better, it might be more profitable for a malicious miner to jump to another pool or just to mine independently. So this is a typical attack called pool hopping. It's a typical attack on a mining pool. Okay, let's talk a bit about security of closed ledgers. As we mentioned in the second, it was the second day, the security of closed ledgers is different, the trust model is different. No denial of service attacks from within the consortium. So this is the illustration which we saw in the beginning. But the model between consortium blockchain and open blockchain is different. And attack model in the consortium environment may include bugs, hacks, misconfiguration, priority responses. All of this is covered by Byzantine behavior. So those protocols such as Smart BFT in Fabric or PBFT, which Fabric was using in the past, the classic BFT protocols, they cover all of those attacks. So they protect against all of them. Double spending, well, we have already talked about double spending a lot, so probably no need to repeat it, right? Unless you have questions about it. So this is just double spending in Bitcoin. But the next one we have not spoken about. We have not spoken about yet. So I'll spend some time talking about selfish mining. What is selfish mining? The basic idea of selfish mining in Bitcoin and other cryptocurrencies is that the malicious attacker, well, attacker is not malicious, it's rational. It's trying to gain, it doesn't try to break the system down. It tries to gain some profit from the system, more than what it would gain if the attacker were mining honestly. How does the attacker do it? The attacker keeps a secret chain and tries to mine in secret. And if the attacker's chain becomes long, it would start, at this point, it would start to release the blocks in order to overcome the main chain. If, however, it is losing, meaning that the main chain becomes longer than the secret chain, then it would abandon the secret chain would reset to the global chain, main chain, and then would create another selfish chain. So it's interesting that this attack succeeds. It's interesting that this attack can be more profitable than money honestly. So let's see. First of all, the details. How exactly it's done? So the initialization. Public chain, we just memorize public chain and create private chain. Then we always watching the difference between the in terms of the length of the private and public chain. So initially private chain length is 0, meaning all, because we just took the chains from the blocks from the public chain, right? So initially it's 0. And then we mine on the head of the private chain. Then there are two events possible. Either the selfish miner manages to find a block on top of the private chain, or the other miners are able to find a block, in which case the new block becomes part of the public chain. So let's see how these two events are handled. So it's like event-based programming, event-based algorithm with two events, and accordingly two handlers. Okay, the first handler, line 6, what happens when my pool, or I, the selfish miner, found the block? Then then I compute the delta. The delta is the difference between the length of the private chain and the length of the public chain. Then I append the new block to the private chain, and I increase the length of the private chain. I increment it by 1. And now the interesting part. So what do I do next? If the difference in the length was 0 previously, and the private brain chain, the length is 2, so previously it was 1, but now I found the block, now it became 2, then I publish all blocks of the private chain on the public chain, and I make the length of the private chain 0. So so previously the delta was 0 before I found the block, so now the delta is 1, so I should be winning, right? And if I'm winning, then I just flood the network with the private chain, and the private chain overcomes the public chain. Okay, so the other handler, what happens if the others, the honest miners, have found the block? In this case, again, I calculate the delta. I append the new block to the public chain, according to the longest chain rule. And then I am looking at the delta, and if the delta is 0, so now the delta became 1, right? Depends how you know. The delta became -1. Now the public chain became longer than the private chain. In this case, I simply adopt the public chain and start mining on top of the private chain, which is created from the public chain. If delta was equal to 1, it means that previously I was overcoming the private chain was overcoming the public chain by the length of 1, but now they are of equal length after the others found the block. Okay, in this case, what do? I publish the last block of the private chain, and then I compete with the block of the public chain. So now there is branching. There are two branches of the same length, that of the public chain and that of the private chain. So it's unknown who wins. The third case, if the delta was previously 2, meaning the private was longer than the public by 2 blocks, then what I do, I publish all on the private chain. So all of the private chain. So if the private chain was 2, but now the public chain is catching up, at this point I still, like after the new block, I still have the advantage of 1 block. Delta was 2, now the delta is 1. At this point, I release all of the private chain and overcome the public chain. Else means the delta was even bigger previously. I only publish the first, and now like the 1 block was found by the public chain. What do I do as a selfish miner? I publish the first unpublished block in the private chain. So that's this is the entire algorithm. Now, how does it work, or why does it work? It works because most likely I am going to lose. Why? Because my power is not 51%. So most likely the published chain will be getting faster, will be appended faster than the private chain. The reason why it's still beneficial for the selfish miner is that in those less frequent cases when I win, I gain a lot. So, so to analyze the performance of the algorithm, the authors built a Markov chain, assuming the memoryless model, MM1. And they modeled the performance of the algorithm using 2 variables. Alpha is the fraction of the computing power that a selfish miner possesses. And gamma is the ratio of honest miners that choose to mine on the pools block. What does it mean? This pertains to this case. So in this case we have branching. We published the last block of the private chain. Now we have 2 branches. So the assumption is that in this case, gamma is the fraction of the honest miners that choose to mine on the pools, on the selfish chain, selfish branch, and not on the honest branch. Now, these are the states of the Markov chain, and the states are modeled by like 0, 1, 2, 3. Those are the delta, the difference of the length between the private chain and the public chain. So, for example, if I'm in state 2, then with probability alpha, I'll go to state 3. Probability alpha, the length, the advantage would increase from 2 to 3. And with probability 1 minus alpha, it would decrease to 0. Why would it decrease to 0? If we are in state 2 and the honest miner find the block, then I release all 2 blocks. I overcome the private chain, the public chain, and then I go back to state 0 because I release all the blocks. So now it's 0. If I'm in state 3, then with probability alpha I go to state 4, and with probability 1 minus alpha I go back to state 2 because I release. Okay, 1 minus alpha pertains to the case when the honest miner find a block. And if they find a block, what do I do as a selfish miner? I release just 1 block from the private chain. So now the difference becomes 2. And what's interesting is that there are two states for zero, right? One state for zero is when the private chain and the public chain have length 0, so there is no private chain. And another case for state 0 is when the length of the private chain is 1 and the length of the public chain is 1. And that's probably the most important state, this one. This state means that the private chain had an advantage of 1, and okay, now the public chain found the block. Now the delta is 0. So what happens next from this state? From this state, we can only go to the state of there are two cases. Either the public chain finds a block and then the selfish miner abandons the attempt, or the selfish miner finds a block. In this case, the selfish miner releases the next block and wins the race and goes to this. So in both cases, it would go to this state, but of course the gain would be different. So this is how the selfish mining attack is analyzed. Now let's take a look at the results of the selfish mining attack. This plot shows the revenue for the selfish miner for different values of alpha and gamma. And there is also the plot for honest mining. So this straight line is for the honest mining. And the straight line indicates a linear dependency between the power of the selfish miner and the gain relative revenue of the selfish miner. It's just a straight line. The more power a miner has, the more blocks it would mine, right? That's simple. The other lines are for the selfish mining, and they depend on the value. So the dependency is on alpha. This is alpha here. But we have different lines for different values of gamma. It's interesting that if gamma is equal to 1, then honest miner, selfish mining is always beneficial to honest mining. So there is no reason to do honest mining if gamma is equal to 1. Gamma equal to 1 means that, okay, it's honest miners found the block, and then the selfish miner releases immediately previously found block. So now we have the branching. And gamma equal to 1 means that everyone adopts the branch from the selfish miner. No one adopts the previously published branch from the honest miners. Of course, this is unrealistic. This is an extreme case. In reality, it's much more common that gamma is close to 0. So what happens if gamma is close to 0? This is the curve. It's the bottommost curve for gamma equal to 0. And in this case, you can see the intersection between the straight line of the honest mining and this curve for the selfish mining. And the intersection is about like around 1/3, 0.33. So it means that below 0.33, if alpha, the power of the selfish miner, is below 0.33, then honest mining is better than selfish mining. But once we go above the power of 0.33, 1/3, then the selfish mining becomes more beneficial than the honest mining. So it means that like we don't need 51% for the attack. We can do the attack with 33%. This is the bottom net result of this analysis. And if gamma is equal to half, which is the middle curve, then selfish mining as the strategy overcomes honest mining as a strategy when alpha is 1/4, 0.25. So the closer gamma to 1, the easier it is for the selfish miner to or selfish mining is a strategy to overcome honest mining. We have another related plot. It's the minimum value of alpha to beat honest mining, right? So the dependency on gamma, so here are different values of gamma. And here's the threshold alpha, which is the minimum value of alpha to beat honest mining. So you can see that when gamma is equal to 1, already, basically there is no need for any alpha. Selfish mining is always beneficial, regardless of the power of the selfish miner. But when gamma is equal to 0, selfish miner need 1/3 of the total mining power of the network. Okay, so by the way, I spent some time on selfish mining because this is what I'm going to demonstrate in the tutorial session, which would be not today, but next day, on Monday. So on Monday, the tutorial session will be dedicated to the simulator. And one of the things the simulator can do is to show the gains due to selfish mining under a variety of conditions. All right, the next attack I'm going to consider as detail is called attacks on maximum extractable value, or MEV. So what's the basic idea? The basic idea is very simple. Due to mempools, the users can preview the transactions before, so they can know about future transactions before those transactions are included in the ledger. For example, in the mempool, there is already a transaction from Alice. I am buying 100 Bitcoin. Wow, that's a very large number. Okay, so now I can anticipate. Most likely after this transaction, the price of Bitcoin will go up. So maybe I can exploit it. How do I exploit it? I can put my transaction just before this transaction. So I'll buy a few Bitcoins. Then Alice will buy a large number of Bitcoins. The price will go up. Now I sell the Bitcoins, I gain profit. This is a classical example of MEV attack. How do I exploit it? I can reorder, maybe I can try to reorder transactions within the block or across the blocks. I can inject new transactions at exactly the right point. And okay, so how those attacks can be launched? They can be easily launched by a miner who can just put the transactions within the block in a certain order. Or it can be launched by anyone paying a high transactional fee. If someone pays a high transactional fee, it's very likely that this transaction will go before a transaction from Alice, in all likelihood. And by the way, this type of attack on MEV can be applied to both open and permission blockchain. Well, not to Fabric, because Fabric doesn't have a currency, but some of the permission blockchain have their cryptocurrencies, and MEV can also be applied there. There are three types. I mean, this is just basic classification. Three types of MEV attacks. Front running. You place your transaction right before the victim transaction. You can have back running. You place your transaction right after the victim transaction. What's the point? The point is that you're the first after this transaction. Because now, like, if the transaction is known to everyone, then well, now everyone knows the price of Bitcoin, and everyone can exploit this transaction. But you're the first. You are guaranteed the first place among those that come after. So that's back running. And sandwich means that you do both. You do some pre-transaction and post-transaction. Okay, so why is MEV so bad? What are the security implications of MEV attacks? Well, of course, Alice, poor Alice will be, okay, maybe not Alice, but like, well, Alice may be losing money as well, because now I place my transaction would also raise the price of Bitcoin. Now Alice will need to pay more. That's the basic example. So it's unfair towards Alice. But it's not the only problem. What happens is that now we have MEV searchers. MEV searcher is a node which scans incoming transactions and looks for opportunities to exploit them. Okay, so now we have a lot of competition, not between the miners, but between MEV searchers. And that competition drives a lot of things up. So, for example, it increases transaction fees. As I mentioned, the most common technique to guarantee that the front running is to give a high fee to the miner. And we have a lot of MEV searchers competing with each other. So each of them wants to be the first. That drives the fees up. Also, suddenly we have a lot of transactions. Suddenly there is one transaction from Alice, and now there is 100 MEV searchers, and each one issues a transaction. Suddenly we have 100 transactions at the same time. The result is network congestion. Not only this, it has been shown that MEV can also destabilize consensus algorithm. So what's the reason why everyone adopts the longest chain in Bitcoin? Why does no one want to violate the longest chain rule? The reason is that it's beneficial to stick to it here, to the longest chain rule. If I mine on top of some other block, then most likely I'll be mining in the losing branch. So what's the point? So it's all about incentives. It's beneficial for me to mine on top of the longest, because most likely this is what the others would also adopt. However, now assume that the fees for MEV become higher than the block mining reward, which incidentally has been shown to be the case for some specific cryptocurrencies, for some specific transactions, for some specific cases. So it's not far-fetched, it's not unrealistic. The fees, normally the fees are much lower than the block creation reward. But in case of MEV, because of financial incentive, suddenly the fees can become very high and can compete with the block creation reward. If that happens, then high fee blocks shift the incentives away from the longest, heaviest chain. Because now, suddenly the miner or sort of the individual miners may adopt not the longest block, but the block that gives the highest fees to them. And if it turns out that for many is the case, then there might be a split. Someone would go with the longest chain, but sufficient number of miners will go along with the block that gives them the best fees. Or maybe not necessarily the best fees, but the best, say, the best increase, like put their transaction in. They managed to put their transaction in as part of front running, and that gave them such a big advantage that it totally overcomes the advantage of block reward. So it has been shown that it may destabilize consensus this way. And there is also a risk of centralization. So why is there a risk of centralization? Because it has been shown that you need sufficient resources to be a successful math searcher. You need to quickly search for opportunities, maybe use even AI to this end, and then you need to pay high fees. So you need to have a lot of funds to launch a math attack. So not every simple user is able to do that. Only a few stronger users are able to do that, and as a result, we may end up with a centralization in the network. Okay, so how do we protect against math attack? So there are three classes of countermeasures: math auction platforms, time-based order fairness, and context-agnostic ordering. The first one is probably the most interesting one. So the second and the third one, they are trying to prevent math. The first one says, no, math is fine. We cannot prevent math. So the best we can do is to make math legal, but also very transparent. So we'll know when math is going on. So the first idea is to create explicit math auction platforms in which math searchers would be competing with each other, placing bids, and the miners would be accepting those bids. So a miner who found the block would be accepting bids from individual math searchers. And the whole process would be transparent for everyone to see. And the process would also be more efficient. So there would be no like hidden jumps in network traffic and congestion. So instead of trying to prevent it, we are trying to regulate it. That's probably the right word. And as a matter of fact, interestingly, this is the most common approach taken by cryptocurrencies. So while there have been more methods proposed on prevention, it turns out that those methods are expensive and maybe not always practical. And this is why regulation is actually a more popular approach than prevention. Okay, so what are the two methods on prevention? The first one is time-based order fairness. So we try to derive the order of transactions. So we try to make it not arbitrary, but to make it derived. So for example, by using some verifiable computation, again, cryptographic primitives, we can derive a verifiable order of transactions based on the history. So now there is no, or at least there is very limited possibility to affect the order and introduce math. So that's based on state machine replication, because every miner would compute the same order in the same way. Yet another method for preventing math is what's called content agnostic ordering. So the ordering operates on metadata. The transactions are not released. The transactions are encrypted. But so the ordering is performed on the commitments, not on plain text transactions, but instead of encrypted transactions or on transaction IDs, which is metadata of transactions. And once the ordering has been established and publicized, at this point the transactions would be themselves will be disclosed. The content of the transaction would only be disclosed to the entire world. I mean, obviously not to the participants, but to the entire world, only after the order has been established. So that's the idea behind content agnostic ordering. And this is still a very hot field, with so many papers, but also so many ideas introduced in the systems. So content agnostic ordering is considered more efficient than time-based order, but on the other hand, time-based order is more provides a higher degree of security. And that concludes the lecture on security on blockchain.